In section 4.2, we're going to talk about the method of substitution for integrating functions. This method is highly useful for integrating function compositions, and it will enable us to actually be able to integrate more complicated integrands. So that's what we would like to do in this section. Now, as far as formulas or any theorems, we don't have any. All we have are these guides that you're looking at when we use integration by substitution. So notice the form of integrand here is important, is that it's in the form of a composition of f of g of x. And then next to that, you have g prime. And of course, remember dx here. At this point for us, dx means the variable that we are integrating with respect to. So for example, just to clarify that, suppose I have wxy and this is dy. So that means in this integration problem, the variable is y that we are integrating with respect to. So w and x are treated as constants. So I can even bring them outside of the radical. There you go. But if this, for instance, if this is same integrand, wxy, and then I have dx, I can no longer bring w and x outside. I'm sorry, not dx. I can still bring w outside and the y this time, but I cannot bring x outside. The variable of the integration cannot be brought outside of the integral. Okay? So again, if I have x times sine x dx, for instance, for something like that, I cannot write it as x sine x dx. This would be flawed. Yeah, because we can only bring constants out, not variables outside of the integrand. Okay. Now, having noted that, these are the guidelines as how to actually proceed with substitution method here. In our first step, we're going to let a new function u be a function of x. And of course, this g of x is part of the integrand. Notice it's typically the inside function. That's what that is. And next to that, you have to have g prime. Okay, and if we don't, of course, we cannot use this method, right? Then we may have to use other methods. So let's actually go through and do this. I'm going to do 10 exercises. I think that's a reasonable number for a reasonable length of lecture. So we're going to take a look at problems number 2 and so forth. In the first 6 exercises, they will actually give us the appropriate substitution here. You see that? So we don't have to search for it, look for it. But then later on, that will be taken away from us. We actually have to initiate what we would like to let u as a function of x to be. So let's begin with exercise number 2. Okay, in exercise number 2, we have x squared times the cube root of square root of x cubed plus 2 dx, and u is x cubed plus 2. Okay, so here we go. Beginning with exercise number 2. In number 2 again, we want to evaluate the indefinite integral of x squared times x cubed plus 2 square root of that, and then dx. Our u substitution, you notice u here is a function of x. Okay, and this we are told to choose x cubed plus 2. So what we're doing actually when we introduce u here, we are introducing a whole new variable. And in fact, we're making a mathematical transformation. So next step is to do du dx. That means we're going to take the derivative of u with respect to the variable x. And derivative of x is going to be x cubed plus 2. Okay, that's what that is. And then from this, we can write du is equal to x cubed plus 2 times dx. Okay, and there we have it. Now let's go back to our integrand, and we're going to replace the variable x with variable u. if you note, the radicand here is x cubed plus 2, which is u. So we can actually write this as, oh, something I didn't do here. So I apologize for this. I said take the derivative and I didn't do that. Sorry about that. That's 3x squared. Okay, so this is going to be 3x squared dx. Okay. Now going back to the integrand, so I can write the radicand as u, and if I look at now x squared dx, I can see x squared dx here, right? The only thing we don't have is the 3. So a couple of remedial action here, because we have to have exactly what's in the what is in the integrand. So I cannot just write du. That would be incorrect, because du does not substitute x squared dx. True? So here's the couple of remedial actions. Some people, what they do is they actually build the integrand to, so where it looks like du, what du needs to be. And this is how it will be built. So if I go, for example, 3 times x squared dx, why 3? Because I see a 3 here. Now I cannot just multiply by 3, so I'm going to pre-multiply by 1/3. So the effect is multiplying by 1. And when we do that now, the combination of 3x squared dx, all of that represents du. You see how that works? So then I can write this as 1/3, the integral of u to 1/2 du. And that's all that is. So the integral of u to 1/2 using the power rule of integrals is going to be u to 1/2 plus 1 divided by 1/2 plus 1. And don't forget the constant of integration. And because I have switched to u, I'm going to personally call that C1 for now, because that's the constant that works with the variable u. Now if I clear this thing up a little bit, 1/2 plus 1, that's 3/2 in the denominator, right? Which in turn turns into 2/3 once we invert and multiply it, and that's going to be u to 3/2 plus this constant. That's resulted by integrating u. And at this point we have 2/9 u to 3/2 plus our constant. Now this is not the answer. Almost there, but not quite. The reason is because we started with our integration variable was x. So what we need to do, if I call I the integral of the original integral, then now I need to replace u with x cubed plus 2, the function of x, to 3/2 plus c1. Okay, now, and actually here what I can do is actually change this now to c2, because this is now a constant that goes with this new variable. But then let me also mention that in the book they do not do that. Okay, in the book they just go c for the constant. So at this point I'm just going to call it, instead of c2, call it a c. And note that those are different constants. Okay, so there we have it, the answer to this integration problem. Now I did mention that there are a couple of remedial actions to get around not having du exactly that. So one way is to build the integrand as we did, as you can see right in here. I built it by multiplying it by 1/3 and then timesing it by 3. The other thing I could have done is I could have actually created x squared dx right up here. So in this case, if I divide both sides by 3, du over 3 is equal to x squared dx. And now I have directly x squared dx in there. See that? So let me now approach it this way and then see how things would be different. Okay, so same problem number 2 we're doing. Therefore, the integral of x squared, square root of x cubed plus 2 dx. Remember, dx, x squared, is going to be du divided by 3. And the integrand is the square root of u times 1/3 du. That's what du divided by 3 is. And this will give me, I can bring the constant outside of the integral of u to a half du. Now that integral, this integral is exactly what this one is. You see that? So your next steps will be exactly the same. I just want to show you how you can get around the fact that your du does not directly turn out to be what's in the integrand. Okay, and there we have it. So we're done with number 2. Next exercise we're going to look at was number 6. In exercise number 6, we're doing the integral of sine x over cosine squared x and then dx. Okay, now for this one, again, we need to see this as a composition. So, and I'll show you the composition here in a moment. But for this one, we are told to choose, we're going to let u be, this is given in the exercise, u be cosine x. Okay, so with that, now I need to do du. And du's derivative of cosine is going to be negative sine x, and then don't forget dx. So we can write the integrand as the integral, the integrand has sine x dx, but we have negative sine x dx, right? So we can actually rewrite this as 1, and then here is du, but to offset the negative, I can either change this to a -1, so I have negative of du, or again, you can build the integrand to it. Okay, if I build the integrand to it, this is how I would build it. So I'm gonna go negative on the outside. Let me just redo this whole thing here. So I'm gonna go negative on the outside of the integral of negative sine x divided by cosine squared x dx. You see that? The double negative makes positive. So this is what I mean by building the integrand, and that's what I've done. Okay, now at this point I can replace the numerator, right, negative sine x dx, I can replace this one by du. So all of the numerator is just going to be du. And the denominator is our u substitution, which is u squared. So that's like -1 over u squared. Okay, and I want to do the integral of that. Rewrite it with negative exponent, and that's going to make it, the integral of u2 -2 is u2 -2 plus 1 divided by -2 plus 1 plus a constant, and that's going to make it just 1 over u. Negative and negative make positive here, right? So this is just going to be 1 over u plus a constant. And the answer to the integration problem. Now you replace u with your, what you let u be, which in this case was cosine x, and call it a constant c. Okay. And there we have this one. Now, personally, what I like to do is I like to kind of build things in that step. In other words, I would have just multiplied both sides here by negative and write negative of du equals sine x dx. So I don't have to build the integrand. Okay, but again, there are two different ways of really doing the same thing. Okay, next let's take a look at exercise number 10. Now, beginning with this one I'm doing, we're not going to have, no one's going to tell us what the substitution must be, so we have to choose our own substitution. 1 minus 3x to 1/4, right? or 1.4, sorry, 1.4 looked like 1/4 to me. Okay, 1.4 dx. Okay, now this is the composition. Again, how is this composition? Let's say f is 1 minus 3x, and then g is x to 1.4. So if I do g of f of x, then I have g of instead of x, I have f of x, means 1 minus 3x. So that means replace x with 1 minus 3x. True? And that's going to give me 1 minus 3x to 1.4 power. And there you go. That's the composition that we're looking at. So we usually let the inside function be our u substitution. So in this case, f of x, which is 1 minus 3x, I'm going to let u be that. Okay, so with that, du is going to be negative 3 dx. Okay, and then because I only have dx, I don't have a negative 3 outside here, right? So I'm just going to offset, divide both sides here, divide both sides by negative 3, so I get negative 1/3 du is equal to dx. So note, we don't just say du equal dx. Some folks just call it that way, but that is not always true. Okay, so just because you change from x to u, dx doesn't equal du. All right, now we're good. We can substitute in here, and instead of 1 minus 3x, I'm just going to call that u to 1.4 power, and then dx was negative 1/3 du. True? Negative 1/3 of du. And this is going to be negative 1/3, right? The constant comes outside of the integral. And the integral of u to 1.4, we add 1.4. If we add 1 to 1.4 and divide by the result of that. So it's going to be u to 2.4 divided by 2.4 plus a constant of integration. And now 2 times 4 is 8, right? Oh, I'm sorry, that's not the way I've written it. It's 2.4, not 2 times 4. Big difference. 3 times 2.4, that's going to be 7.2. So it's going to be 1 over 7.2. And then let's replace u with the inside function was 1 minus 3x to the power of 2.4 plus a constant. That's going to be the answer. Exercise number 10. Let's take a look at number 16. Okay, in number 16 we have the integral of, this time we have 2x times the cube root of 1 minus 4x squared dx. Notice the form of our integrands are now more complicated than what we had in an earlier section when we first discussed antiderivatives. Okay, so again, for this one, the composition is going to be like this. Let's say I have g of x, which is cube root of x, and then I'm going to call f of x to be the inside 1 minus 4x squared. Okay, so what we're looking at is actually g of f of x in this case. So that's going to be g of 1 minus 4x squared. You put that inside the radicand, you get 1 minus 4x squared. Okay, so there's our composition. So I'm going to let u be 1 minus 4x squared. And in this case, du is going to be negative 8x dx, right? Now let's look at the integrand and see which components of du are present. So we have dx and we have x. Instead of negative 8, we have 2. Okay, so if you want to build the integrand, you can multiply the integrand inside by negative 4 and outside by negative 1/4. But remember, I like to sort of build to what's in the integrand, right? So I'm going to divide both sides by negative 4 here. By negative 4. And if you look at the right side, I have what? 2x dx, correct? And that's precisely what the integrand has. So instead of 2x times dx, we can replace it by 1/4 du. Okay, and what I'm going to do is I'm going to put negative 1/4 because it's a constant outside. The cube root, I'm going to write it as u to 1/3, and then this is du. And there you have it. See, suddenly the integrand becomes much easier to work with. So this is going to be negative 1/4. Now again, using the power rule, 1/3 plus 1, that's going to be 1 and 1/3, which is 4/3, divided by 4/3, plus some constant of integration. So the answer now, invert and multiply 4/3, we get 3/4, so that's going to give me 3/16 of 1 minus 4x squared to the power of 4/3 plus the constant of integration. And there we have the answer to number 16. Okay. So as long as we just follow through with the process and take it one step at a time, I don't think it's too complicated. At least not yet. Now sometimes they get tricky and you gotta become more creative, especially with trig functions, maybe use identities, so on and so forth, but for the algebraic ones, they're not so terrible. Okay, the number 22 now, we're gonna do the square root of 1 plus u to negative 1 divided by u squared, and then du. Okay, and also let me mention sometimes there's more than one substitution that will work. More than one substitution that will work. It's just a matter of one being superior to the other in that there are fewer steps in manipulation. But there's more than one way to do a substitution. Okay. So for this one again, I'm going to go with the inside function, and this is the variable is u. So I cannot say I'm going to let u be 1 plus u negative 1. See, we cannot have the same variables. That's not the true statement. So if I write it like that, that's not right. So because the problem is using variable u, I'm going to use a different variable, call it m. Let m be 1 plus u to negative 1. Therefore, dm is going to be negative 1 u to negative 2, which means that's negative 1 over u squared, right? That's what dm is. Now, looking at the integrand is in the form of du over u squared, true? And then, of course, du here. When we take the derivative, there's going to be du here. So I almost have the integrand, right? What I don't have is the negative 1 in the integrand. But we can create that, true? We can make it. Or I can multiply both sides here by negative 1, and that's going to make it 1 over u squared du. Now, the integral is going to be that of square root of the radicand, that's just the square root of m, isn't it? And du over u squared, du over u squared. You see that? That's just negative dm. So I'm going to replace that by negative of dm. So that means I need to put negative outside the integral symbol, and that is dm. Okay. And the integral, of course, of m to 1/2 dm is what we're doing. Using the power rule, that's going to be m to 1/2 plus 1 is 3/2 divided by 3/2 plus some constant. And that would equal to negative 2/3 m, which is 1 plus u to negative 1 to 3/2 plus a constant. Okay. And again, I want to mention or emphasize that in the books in general, they don't do this, call these two different constants. So as long as it's a constant, they don't care that there are two different constants, because when you take the derivative of all constants, they're all going to be 0. So it doesn't matter what these constants are. Not at this point. With indefinite integrals, they don't matter. The constants of the integration don't matter what the numerical value is, because we're looking at a family of antiderivatives, so all of them work. Okay, then there you go, number 22. Let's move on to number 28. In exercise number 28 now, for this one, the integral is that of x sine x squared dx. Now note in here, the squared is on x. It is not like this is how they write powers of sine, right? Okay, so just want to clarify this. It makes a big difference which is which. So for this one, I'm going to let u be x squared, and therefore du is going to be 2x dx. Now I see x dx, so that means 1/2 du is x dx. Okay, now let's do this. I'm just going to write this as, well, sine x. Remember, I did not let u be sine x, it's just x squared. So that's sine u, but then x dx is 1/2 du, right? So the constant we always put outside, and then here's du. And we proceed with integration. The integral of sine is going to be negative cosine plus some constant, and that's going to be negative 1/2 the cosine of u, and u is x squared plus a constant. And there we have it, number 28. Okay, pretty, again, straightforward. Let's do number 32. In exercise number 32 now, the integrand is, we're going to find the integral of the integrand being cotangent cube x, not x cubed, but cube x, cosecant squared x dx. And there you have it. Now, for this one, it's a little maybe harder to see the composition, because you can view this as a multiplication, right? That's what that is. I have cotangent cube x times cosecant squared x. So I'm gonna let u be cotan x. Okay, and you'll see why in a moment. Du is going to be what? Derivative of cotan is negative cosecant squared, right? X dx. And that is why. You can see that? So we have cosecant squared x dx, and for that reason. Now, if I had let u be cosecant x, then du would be derivative of cosecant, which is negative cosecant x cotan x dx, right? And when I try to substitute into my integrand, so this is going to be in the form of negative, right? And cosecant cotan dx, well, cosecant cotan dx are there, right? And so cosecant x cotan x dx, all of this is just going to be negative of du, right? So that's going to leave me with cotan squared x, right? Cotan squared x, and yet another cosecant x. Okay, so I can now write the integrand as negative. Well, I have a cosecant, so that's u, so there's my u du. But then you see that I have a cotan squared x here. Cotan squared x. So the question might be, well, what am I going to do with that? How am I going to handle that, right? And that's the trouble. Now at this stage, of course, we could use the identity that connects cotangent, right, and cosecant, and maybe I'll do that. But you see the complexity here? That's why I was saying that some choices are better than other choices. So in this case, what I have selected for you is going to work out very nicely. So the integral is going to be negative. Well, cotan, that's going to be u cubed, and cosecant squared x dx, all of that is just going to be du. See how easy that is in one step. The integral is 1/4 u to the 4th plus a constant, and the final answer is negative 1/4 u is cotangent to the 4th x plus a constant. There, that's what that is. Now, if I do it using another substitution, first, the identity that I need that connects cotangent and cosecant. So, if I divide everything by sine squared x, I get cosecant squared x is 1 plus cotan squared x, right? So that means cotan squared x is cosecant squared x minus 1. So keep that in mind. So same exercise we just did. Now let's do it again. The integral of cotan cubed x cosecant squared x dx. This time I'm going to let u be cosecant. Okay, cosecant x. And if I do that, it's going to make it more complicated. And here's how. Negative cosecant x cotan x dx, right? And again, when I rewrite this integral, well, cosecant squared, that's going to be u squared. Oh, but I don't want to do that. I want to see cosecant cotan dx. So if I look at just one cosecant, remember I have two to play with. So just one of that dx and cosecant, and I have one cotan, so pull one cotan out of 3 cotan out, and this way I have secured my du, right? But it's going to be negative of du, right? So this is going to be equal to negative, and here's my du. Now I have 3 cotan to work with, so that leaves me out with a cotan squared, right? But then remember, cotan squared here is cosecant squared minus 1. So I'm going to write this as, because cotan squared x is cosecant squared minus 1. Cotan squared x is cosecant squared x minus 1. But then remember, cosecant, isn't that our u substitution? So therefore I can write cotan squared x as u squared minus 1. That picks up the other 2 cotangents. I still have one cosecant, right? Because I had 2 cosecants. One of them is absorbed by du, the other still at large. And there we have it. And look how much more complicated this is getting, right? Or it has gotten. It was a lot easier making the original u substitution, let u be cotan. Now, but let's proceed with this. So this is going to give me negative of, I'm going to move that negative inside, this one inside. So that's going to be the integral of, and distribute. So I get u positive, and then negative u cubed du, right? I distributed the sign, that's how I got these to be negative and the other one positive. Okay, so this integral of u is going to be what? 1/2 u squared plus or minus 1/4 u to the 4th plus a constant, right? And remember what u was in my selection. U is cosecant in this case, right? So this is going to be 1/2 cosecant squared x, right? Negative 1/4 cosecant to the 4th power of x, right? Okay, and for this one, let's see. I can rewrite, okay, remember cosecant squared. Cosecant squared is cotan squared plus 1, right? Cotan squared plus 1. So I can write this as 1/2 cotan squared x plus 1 minus 1/4 cotan squared x plus 1 to the 4th power, right? Now, instead of raising this to the 4th power, actually what I can do is I can factor cosecant, right? Let's factor in here. I'm going to factor 1/2 cosecant squared x. So that's just going to give me 1 minus 2 cosecant squared x. Okay. And, oh, actually, yeah, 1/2 factored from 1/4 is going to be 1/2, not that. There you go. When you redistribute, it's going to work out. Okay, and then we can replace cosecant with cotangent at this stage. So this is going to be cotan squared x plus 1 times 1 minus 1/2 cotan squared x, right? But you can notice how much more complicated this is getting, right? And what I'm trying to do here is I'm trying to get this answer. Okay, that's what I'm showing you. And we'll get there eventually. Okay, so anyway, we're not going to keep playing with this one, but I just want to show you again an easy, a good choice of a substitution and a not so good choice of a substitution here. And anyway, so we're done with that exercise. Let's take a look at our next exercise. So this was the one we just did, was number 32. Our next one is going to be number 38. In exercise number 38, we have I is equal to the integral of sine of root x divided by root x. Okay, and then dx. So for this one, I'm going to let u be the argument of sine. That's the composition sine of something. So let u be root x. Therefore, du is going to be, remember, that's x to a half. So derivative of that is 1/2 over 1 over root x dx. And as you can see, we do have dx over root x. What we don't have is a half. So if I multiply both sides by 2, I get 2 du is 1 over root x dx. Okay. And now we can make our substitution. So this is going to be 2 times the integral, 2 because of that. And there you go. So 2 du, that's, these two are going to replace dx. Okay. And sine of root x divided by root x, well, that, remember, dx over root x is already gone due to du. So all that is just sine u. And the integral of sine is going to be negative cosine u plus a constant. So that's going to be negative 2 cosine of u is the square root of x plus a constant. And there we have this one, number 38. Number 42 In number 42, the integral is that of secant squared x plus 1 times the square root of 1 plus tangent of x plus 1 dx, right? Now, for this one, because we know the derivative of tan is secant squared, and we have that on the outside, so we're going to let our u, it makes sense for u to be 1 plus tan of x plus 1, right? And again, here's why, because du is going to be secant squared x plus 1 dx, and that is why. Of course, chain rule, the derivative of inside of x is 1. So this is going to equal to secant dx, that's just du. So this reduces suddenly to u to a half du. So it's quite easier than the one we started with. And this is going to be 2/3 u to 3/2 plus a constant. And the final answer, remember we started with variable x, so we're going to end up with that same variable. The answer is 2/3 tangent of x plus 1 to 3/2, right? 2 3/2 plus a constant. We can also write this, by the way, as tan x plus 1 square root of cube plus a constant. Now, the reason we might want to do this is because a lot of times we would like to preserve the format of the integrand in the answer, if they are compatible. So because the integrand had the square root, so the final answer will have square root in it, like that. But both of these are acceptable. I just want to show you that usually that's what happens. They like to preserve, again, the shape of the integrand as much as possible in the final answer. Let's get number 44. In number 44, the integral is 1 plus sine x divided by cosine squared x dx. Okay. Now, for this one, because if I make a u substitution, like for example, we have cosine squared x, like, so if I let, for example, if I let u be cosine x, and du is what, negative sine x dx, which is good, right? We have it in the integrand. But then the 1 plus, if we didn't have the 1 plus, we would have done that. Because it's 1 plus, so we need to do something different. And that something different is, let's divide individually by cosine squared. So we have 1 over cosine squared x plus sine x over cosine squared x dx. And now that substitution that I was thinking I was going to work out nicely, right? So the integral becomes that of secant squared x dx plus the integral of sine x over cosine squared x dx. Right? Okay. Now, let's make our u substitution. First, the integral of secant squared. That's easy. That's tan x. Right? So let's handle the integral of sine x over cosine squared x here. If I let u be cosine x like I did before, du would be negative, or simply sine x, right? Derivative of cosine is, negative sine, sine x. The derivative of that is, negative sine x, right? And dx. Okay. So that means negative du is sine x dx. So this is negative 1 over u squared du. Okay. And the derivative here is going, the integral here is going to be what? Negative integral of u to negative 2 du. it's going to be u to negative 2 plus 1 over negative 2 plus 1 plus a constant. So that's negative. Well, double negative here makes positive, right? Because denominator is negative 1. So it's going to be u to negative 1 plus a constant. And u to negative 1 is 1 over u, isn't it? Plus 1 over u plus a constant. And there you have it. Okay, and that's number 44. Let's take a look at number 48, the last one in this section. In number 48, the integral of x plus 1 divided by square root of x minus 1 to 3/2 and then dx. Okay, so let's see, what should we let u be in this one? Again, the more complicated portion of this integrand is that, right? So that's what we want to substitute for. So looking at just the denominator, we see this as a composition of something to 3/2. The inside function, that's what we're going to let u be, right? So I'm going to let u equal square root of x minus 1. Okay. Now, notice in the numerator we have x plus 1. When I do du, du here, what am I going to get? I'm going to get 1 over 2 square root of x dx, right? Because derivative of negative 1 is 0. That's 0, right? Its derivative is 0. And let's see. So look at in the denominator though, that's going to be u, right? It's going to be u to 3/2. But judging from our dx, we don't have what you see here up here. We do not have that, right? So for something like this, I mean, I'm going to keep that, but we're going to actually solve for square root of x. That's going to be u plus 1, true? And then if I square both sides, I get u plus 1 squared. True? Now, let's try and see how this is going to work out. So the integrand is going to be, well, x plus 1, that's going to be u plus 1 squared plus 1 all over. What's the denominator? Denominator is going to be u to 3/2. True? U to 3/2. Now, we need to find out what dx is, right? What dx is. So in this form, if I take the derivative, you can take it this way or this way, doesn't matter. If I take the derivative here, I'm going to get dx is equal to 2 times u plus 1, the power rule, and then times du, right? And therefore, dx is 2u plus 1 du. Now, if I do it this way, multiply both sides by 2 square root of x, I get 2 root x du equal dx. But then square root of x, right? Remember, u is root x minus 1. So square root of x is u plus 1. And we have it up here too, right? So if I substitute, for square root of x, u plus 1 du, I'm going to get exactly the same expression. You see that? And that's equal dx. So however you do it, that's what dx is. So we're going to replace dx with 2 parentheses u plus 1 du. That's the numerator, right? Times 2u plus 1 and then du. Okay, and now we have everything in terms of u. And of course the integrand looks pretty sophisticated by now, correct? But we'll simplify it. And all I gotta do is in the numerator, within the bracket, if I span the binomial, I get u squared plus 2u plus 1, and then there's already a 1 in there, right, times 2u, which I can bring the 2 outside. This 2 comes outside, of u plus 1 divided by u2 3/2 and then du. Okay, so this is going to be 2 times. Now the numerator I'm going to distribute from the right, the binomial to within, and keep in mind 1 and 1 makes 2, so distribution is going to give me u cubed plus 2u squared plus 2 times u is 2u, right? And then 1 times u squared plus 2u plus 2, that's 1 and 1 makes 2, divided by u2 3/2 du. Okay, and then what do we do next? Let's divide each of these individually. Well, I need to combine like terms. Let's do that. Maybe we can get the numerator to become a little easier. Plus 3u squared, and then 2 and 2 makes 4u plus 2. Okay, divided by u2 3/2 du. Now, because we're about to integrate this, let's divide individually by the monomial. Okay, so this is going to be, in other words, the integral of u cubed by u2 3/2. That's going to be u2 3 minus 3/2. That's 6 minus 3/2, right? 3 minus 3/2 is going to be 3/2, right? So that's u2 3/2 plus 2u to 1/2. Okay, let's divide that one. Oh, I'm sorry, I'm over here. I was looking up here. Okay, plus 3u squared by u2 3/2. That's going to give me plus 3. Now u squared times u2 negative 3/2. 2 minus 3/2 is 1/2. So that's 3u to 1/2, right? Plus 4. The next term is 4. 4u divided by u2 3/2. So it's going to be 4u times u2 negative 3/2. That's 4u2 negative 1/2. Plus, finally, 2 divided by u2 3/2. That's 2u2 negative 3/2. So again, individually, I divided by the monomial. And the integral is going to be now the integral of u2 3/2, right? We're going to use power rule on every one of these. Okay. So 3/2 plus 1 is 5/2. So it's going to be 2 times. Invert and multiply. 5/2 becomes 2 5/5 in the denominator. u2 5/2. Plus u2 1/2 integral of that would be 3/2. Invert and multiply, we get 2/3. So it's going to be 3 times 2/3 u2 3/2 plus 4 times negative 1/2 plus 1 is 1/2. Invert and multiply, we get 2. And negative 3/2 plus 1 is negative 1/2. Invert and multiply, we get negative 2 u2 negative 1/2 plus some constant, right? And of course the 2 on the outside multiplies with all of them. We are almost done with this one, nearly done with this. All I have to do now is replace and just kind of tidy up the coefficients a little bit, right? So we're going to get 4/5. Remember what u was, the square root of x minus 1. That's root x minus 1 to 5/2 plus 2. Actually, yeah. 2 times 2 on the outside, 2 times 2 makes 4. U to 3/2. Done with that, right? Plus 16 root x minus 1 to 1/2 minus 8. That's 2 by 2 and then times 2 on the outside. Negative 8 and then square root of x minus 1 to negative 1/2 plus a constant. Good? Now I know you're thinking about simplifying this beast, right? We could simplify it, but that's probably good enough. That's as far as we're going to take this one, because then the algebra gets too convoluted. So there we have it. We're able to do these exercises by using the method of substitution. Okay, there are not too many methods of integration, by the way. In Calc 1, which is what this course is, we look at the substitution method, and in your second semester calculus, you'll be introduced to the method of integration by parts. But for now, this is all we want to do. So we're done with this section, and we will be using substitution method, by the way, going forward in a lot of sections that are coming up ahead. But with that, we are done with this lecture.